Good day, I'm Kumar Shankar and I'm here to talk about MRF maps. This work is motivated by how occupancy grids struggle with noisy depth data for robotic planning purposes. Specifically, high incidence angles end up clearing occupied space, and sensor noise is not adequately captured. These drawbacks exist because occupancy grids use a strong and inaccurate independence of cell assumption. Instead, we propose performing joint inference over all voxels traversed by rays using forward sensor models, and this is made feasible due to a choice of framework exploiting GPU compute. So here's a qualitative comparison at 5 centimeters on the noisy augmented ICL NEOM dataset. As you can see on the OctoMap on the left, glancing rays along the walls and along the sofa lead to empty voxels. In addition, surfaces appear to be more noisy in general than the equivalent MRF map on the right. So our contributions in this work are MRF depth ray potentials for joint inference of occupancy, incorporating learned sensor noise characteristics within this framework, a principled evaluation metric for probabilistic occupancy maps, and an open source real-time GPU implementation. We begin by detailing MRF Ray Depth Potentials. Consider a discretized map volume and a depth camera. Corresponding to each pixel, a ray can be traced through this volume. Each cell of the grid that the ray traverses is initialized as an occupancy variable, along with the depth variable corresponding to the ray measurement generating distance. These nodes are then connected by a ray potential factor psi and prior potential factors for the occupancy nodes. Each ray then has its own set of associated nodes and depth potentials. And finally, rays going through the same voxel are explicitly coupled, for instance, by occupancy 9, as shown in this figure. So performing inference involves finding the joint over all the occupancy nodes and the depth nodes. And this is done via belief propagation in our work because it's inherently parallelizable, and we get fast inference since the depth data is directly observed and is consistent throughout most of the views that we see. So iteratively, this goes on by each ray potential sending out messages to all the variables that it's connected to, and then in the second pass, all the variables accumulating the incoming messages and then sending out messages to each connected ray depth potential. Now we briefly detail how we incorporate learned sensor noise characteristics within the framework. Motivated by prior work, we regress quadratic polynomials for sensor depth bias and variance per 20 by 20 pixel block of the depth sensor. This is done using a motion capture arena and a standard calibration board where for each unique pose we accumulate ground truth depth and measured depths. Shown here is a sample of data points corresponding to the selected pixel block for a RealSense D435 camera. To see the impact of incorporating these learned sensor characteristics, here's a demonstration on real-world data collected within a motion capture arena. The depth image is reprojected as a point cloud colored by distance from the camera. Note the noisy nature of the depth images. The real-time inferred MRF map is shown in the top right and the OctoMap on the bottom left. Keyframes are created at fixed geometric thresholds and shown as gray frustums. Note the stark difference in fidelity of representation, especially for the hand of the human subject in this video. We now present a more principled approach than that used for conventional quantitative robotic map accuracy evaluation. Consider a ray traversing a probabilistic occupancy volume parameterized by S, the distance along the ray starting from the camera origin. Corresponding to the two hashed obstacles, ray tracing through the probabilistic map leads to two bumps along the ray. Voxel occupancy here is reimagined as regions of constant occlusion density. As the ray traverses through these regions, the visibility of the next voxel monotonically reduces proportional to the length traveled through the previous voxels. Occlusions along the ray reduce the likelihood of the generating surface for the measurement existing further ahead. This is codified by the probability of the measurement generating surface being a product of the visibility and the occlusion density. A sensor measurement then is classified as being accurately explained by the map if the distance of the maximum likelihood measurement generating surface, denoted here with the star, is within 1.5 sigma of the sensor measurement. Hence, for the measured distance on the left, the map accurately explains it, whereas for the one on the right, the map doesn't. Thank you, and please visit us on GitHub.